Okay, this is 15.3, and what we're going to talk about here, and this is where going back to chapter 11 ties in, which is why I can't totally leave out chapter 11, but I don't have to put it on final. 15.3 is about area and something called the definite interval. And the relationship will become more apparent when we go into the explanation of what a definite integral is. Because we've been doing indefinite integrals, meaning we had to have the constant of integration added on to the end. And the only way we could figure out what that constant was is if they gave us some information that allowed us to plug in and find the value of that constant. This is one of the kinds of problems that we might be solving in this section. If we know how the rate that oil is leaking from the machine, we know how that oil leak varies with time, how could we estimate the total amount of leakage over a certain period of time to know how much oil we're actually losing? The quantity is of much more interest to us in some cases than the actual rate at which it's happening. If the rate's high, of course, it's going to be a higher quantity, but we might need to know that exact quantity. So this is how we're going to start out. This is kind of a visual way of doing this. And everything that you see pop up here may or may not be in your notes. There may be some things that I've left out of the notes because it's to remind me to explain something to you, but it's not something you need to write down. So if you see something that's missing from your notes, it's missing for a reason. If we look at the region bounded by the y-axis, the x-axis, and the graph of f of x is the square root of 4 minus x squared. Basically, 4 minus x, the square root of 4 minus x squared is a quarter of a circle. That actually is what it is. It's 1/4 of a circle. And if we wanted to know what that exact area of that quarter of a circle is, we would have a hard time doing it with geometry formulas if the only thing we have are formulas about rectangles and such as that. So imagine one way that we could figure out an approximation of that area would be if we tried to have one rectangle that we started at the left end point of the interval, and then one that started halfway through that interval. So if we had two rectangles, each one of these two rectangles is going to be 1 unit wide because the total distance from 0 to 2 is 2. So that makes each rectangle 1 unit wide. And then the height of the rectangle, I could plug in x equals 0 and see that the height of this first rectangle would be the square root of 4, which is 2. And I could plug in 1 into that formula to figure out that at f of 1, then I would have the square root of 4 minus 1, which would be the square root of 3. So that would be the square root of 3 tall. So if I add these together, 1 plus the f of 0, which is 2, plus 1 times f of 1, which is the square root of 3, and then do the arithmetic, the approximate area of that rectangle, or those rectangles, is 3.7321 square units. But you can see that that approximation overestimates the actual area that I'm looking for. It's too big. Now, one way to get around that would be, what if I put one rectangle inside the circle? Well, I could do that too if I make it 1 unit wide, and then at this point that's going to be the square root of 3 units tall, because that's f of 1. And the area of that one rectangle is only 1.7321 square meters. But I'm leaving out a little piece there, and I'm leaving out a good sized chunk of it on the other side. So that's not a good idea either. It's not the best idea. So another way that I could do it with just two rectangles is, instead of making it have its height be at the edge of the left edge, maybe if I put it at the midpoint. In other words, I calculate the height of this rectangle to be f of 1/2. And f of 1/2 turns out to be the square root of 15 over 2. And then I would have this f of 3/2 because that's halfway between 1 and 2. And that would give me f of 3/2 is the square root of 7/2. And that's about 3.2594 square units. And if you'll notice here, that's actually a really close approximation because I've got a little bit here that I didn't include, but this little piece here is just about wiped out by that little piece there. And this little piece here is only a little more than wiped out by the part that overestimates. So it's closer. It's better than the other two. Now the other thing I could do is the same idea. I could actually split it and make 4 rectangles out of it. But if I align them at the left endpoints, what happens is that I have 4 rectangles, all of which are 1/2 unit wide. And using x equals 0, x equals 1/2, x equals 1, x equals 1.5, and x equals 2, and doing the arithmetic, it turns out that it's about 3.4957 square units. And there again, I'm back to the fact that I'm definitely overestimating because I've got rectangle hanging outside the circle. But it's still a better estimate of the area probably than the previous ones were. Now what would work even better would be if I divided it up into more rectangles. So if I had instead 8 rectangles for f of 0, f of 1/4, f of 1/2, f of 3/4, f of 1, f of 1 1/4, f of 1 1/2, f of 1 3/4, and f of 2, and that's the heights of all those rectangles. That gets me down to about 3.3398 square units. And notice that the part that's actually hanging outside the circle now has considerably shrunk. It's not nearly as much as it used to be. So that the estimate's getting better. Now the idea here, and I think in your notes, if I remember right, it says, and I could use more and more and more rectangles. What would happen is if I kept increasing the number of rectangles, the amount out here that was hanging out is going to keep shrinking. It's never going to go away, but it keeps shrinking. So that I'll do a little overestimation instead of quite a bit of overestimation, or moderate overestimation as I have here. So the process that we're doing here, and I don't think this is in your notes, or maybe it is. It is, okay. The process we use in this example of approximating the area under a curve by using more and more rectangles to get a better and better approximation can be generalized. What we're actually doing is we're going to divide the interval from x equals 0 to x equals 2 into n equal parts. And since it's 2 minus 0, that's just 2 over n. So each rectangle is going to have a width of 2 over n and a height that's determined by the function value at the left side of that rectangle. Or at the right side, because we could do it with its right endpoint, or even the midpoints. We can do all of those. We could also average the left and the right side values as we, I didn't do it in the examples because that makes too many examples. You get the idea. More rectangles, better approximation. So what we're actually doing here then is we're building this table. So if we used 2 rectangles that were aligned at the left edges, then we got 3.72, very much overestimated. Or if you align them at the right side, then we underestimated by a huge amount. You can totally ignore this trapezoidal because I left those out. Trapezoid says that you use trapezoids instead of using rectangles because a trapezoid has a slanted top and you can make it fit better. And it seems like it would be the best method, but the truth is, when it all comes down to it, that the one that's going to give us the best is going to be the midpoint. Because as I go from 2 to 4 to 8, you can see these This one continues to underestimate. This one eventually gets close, but it takes 500 rectangles to get close. Whereas this one takes 500 to get to the same number, and this one's finally getting close. But the best estimation will come from actually knowing what the actual area is. So the function is y equals the square root of 4 minus x squared is the equation for a circle. If we square both sides, the equation of the full circle turns out to be x squared plus y squared equals 4. And we don't have the whole circle, we only have 1/4 of it. So the actual area of that circle is 1/4 times pi times 2 squared. That's pi r squared, and we have 1/4 of the pi. We have 1/4 of the circle. And 1/4 times 2 squared is 1, so actually it's just pi, and the value of pi is 3.1416 if you go to 4 decimal places. And since you've got it there on your paper, look and see which one of those gave 3.1416. I think it's in the very last column at the very bottom. So your midpoint formula actually works the best. Okay? And in fact, that's actually the way that they discovered the value of pi, was kind of by the same process, but this was, I'm trying to think which mathematician it was. But it was in years before Christ that he came up with this idea of actually cutting those up smaller and smaller. So he was a pretty smart guy. So in the table, the midpoint method gave the closest approximation. And if we were to try to do a curve like this one, if you do 10 rectangles with equal width, notice that you get considerably closer even if you just go to 20 rectangles. Now here's the hitch, and I know you're already thinking ahead. Okay, you're going to want me to do enough rectangles to make my estimation close. Do you know how much arithmetic I'm going to have to do that? You want me to find the area of 20 rectangles, that I have to find the heights of them with an algebra formula every time I have a rectangle. Yeah, that doesn't sound like fun. So in order to develop a process that will give us the exact area, what we have to take into account is that we're dividing the interval from A to B into n pieces of equal width. And each one of those n pieces is going to be the base of a rectangle. So x sub 1 is going to be a point on the first interval, and x sub 2 on the second interval, and so forth on up to the nth interval, because n, we don't know how many we want to make. And in the formula shown, this symbol, delta x, is going to actually represent the width of every one of those intervals. And since the length of the entire interval is b minus a, then each of the pieces has a length delta x, which is b minus a divided by whatever n is. And here comes the calculus. Here's an arbitrary rectangle, and its midpoint is something we call x sub I. There's a whole bunch of them. The ith rectangle's actual area is the function of f sub I times the change in x. In other words, the width of that rectangle. And the width of that rectangle is dependent on n approaching infinity. In other words, more and more and more and more rectangles. And that's where I said chapter 11 comes in. So this is the textbook definition, and I printed it out for you. But in English, what that means is the definite integral is calculated by finding the sum of the areas of n rectangles as n approaches infinity, in other words, the number of rectangles increases without bound, on the interval from A to D, and that's supposed to be just D, not DE, where A and B are values in the domain of f of x. In other words, it has to be an interval where the function is actually defined, which is kind of common sense. So this is where chapter 11 actually was supposed to help you understand that if you take the limit as x approaches infinity of all the areas of those little rectangles, you can do that by using integration. And the definite integral works just exactly like we've been doing problems in section 15.1 and 15.2, except that we're going to have now actual numbers that we can plug into those functions we come up with and figure out what the area between that function and the x-axis is. And that area is going to have meaning for us. And the only thing to keep in mind here is unlike the indefinite integral, which was section 15.1 and 15.2, that's a set of functions, and they differ by a constant. The definite integral actually represents a number, an actual number that means something in context of a problem. So we're going to find the definite integral now and equate that to area under the curve. Now, if you have a TI-84, here's the good news. If you have a TI-84 or an 83, you can get the numerical integral just by knowing the function and the two endpoints. It'll give you that number, okay? But it is helpful always to look at a graph of the function, especially if there's two of them, because sometimes it'll be, and if you have two terms, it's going to be two integrals, and you're going to want to break those up. So it's helpful to actually look at a graph of the function before you make a determination as to what your endpoints are, because those endpoints may or may not be what are stated in the problem. You may have to pick another value in between those two and break up that interval. But this is what you do, and if I were using the TI-84 to solve the problem I just solved, what I do is I start at 0 and I go to 2 by filling in 0 and 2. It's always the beginning from the bottom to the top or from the smaller to the larger. What's on the bottom is the smaller one, what's on the top is the larger one. And then put your function in. And it already supplies you with the d, so what you have to put in is, this is with respect to x. Okay? So you'll plug those in and hit enter, and it will tell you that the answer is 3.141593074, which is almost exactly pi. If you have the TI-83, it works the same way. In fact, it looks a little bit like what we did when we did numerical derivatives. We're doing function integral, and we're going to put in the function, and then put in an x, and then put in your lower value, or a, and your upper value, which is b, and then we get the same exact answer back again.
Can I ask a stupid question?
There are no stupid questions.
On the TI-84,
Some of the TI-84s don't do the way that one showed.
okay, because I don't think I had that point.
Okay, yes, your TI-84 looks just like this.
Then like the 83. Okay.
Some of the 84s are weird because they did some of them one way and some another way. So you need to see which way yours looks, and that's why I showed you both screens there, so you know how to get to what you were doing with both of them. You get to both of them the same way. You hit math and the number 8, I think, or number 9. Yeah, 8's derivative, number 9. So here's an example. Let's see if you can approximate your example, and I'll do it using a formula and let you do it using your numerical integral. But this one says approximate the area from 0 to 4 of 2x dx, the area of the region under the graph, of f of x equals 2x. In other words, that's above the x-axis between x equals 0 and x equals 4. That's what this actually says. Find the area underneath f of x equals 2x that's above the x-axis and between x equals 0 and x equals 4. And we want to use 4 rectangles of equal width, and the heights are the values of the function at the midpoint of each subinterval. Now, this is the hard way. All you have to do is copy, because I didn't ask you to do the arithmetic. Okay? This is the hard way. What you would have to do is, since you're going from 0 to 4, your first interval is going to be at 1/2. Because you're going from 0 to 4, and you're going to cut it up into 4 rectangles. So that's 4 divided by 4. You're going to actually have to go to the midpoint of each of those. So the first midpoint's going to be at 0.5. The second one's going to be at 1.5. The third one's going to be at 2.5. And the fourth one's going to be at 3.5. So what you would do is you would plug into your calculator f of x equals 2x. And then find f of 0.5 and f of 1.5 and f of 2.5 and f of 3.5. Because this is the heights of all of those rectangles. So that's what you're filling in there. Now, pardon my very crude graphing here, please. The line f of x equals 2x has a positive slope of 2. Okay? I'm going from 0 to 4, and I want to know what this area is. Now, in truth, this is a triangle, and its base is 4 units, and its height is 2 times 4, which is 8. And the area, in truth, is 1/2 times the base times the height, which is 1/2 times 4 times 8, and it's 16. So all we're going to do is prove by doing this little table thing that you actually do get the right area, even though this is a straight line, and we can check that out. So what happens here is that we're going to put in these midpoint rectangles. That one's too tall. Ignore that. That one's too tall too. So there's our rectangles. And on every one of these, the amount that's overestimated is going to be canceled out by the amount that's underestimated. It's going to actually come out to be perfect. This area is the same as this one. This area is the same as this one. So this that's hanging out is balanced out by that part that's actually included, okay? So what the calculations are that we're doing is based on that drawing, and they look like this. You're actually adding up for I equals 1 to 4, the value of the function at the first value of x times how wide it is, and delta x in every one of these is 1, because the width of the rectangle is 1, because we're going from 1 to 4 and we have 4 rectangles. And then the heights are different because f of 0.5 turns out to be 1 and f of 1.5 turns out to be 3 because it's 2 times x. So f of 2.5 is 5 times 1 and f of 3.5 is 7 times 1. And it turns out that the summation of the areas gives us 16, which is what the geometry formula says it's supposed to be. So it works in a case where we actually can check it by doing the geometry formula. We don't usually have geometry formulas for things like normal curves. So there's a much better picture of what I was trying to show you. Now the second method that we can do is using the graphing calculator. And you don't necessarily need to know how to do all of this for the next time, but I'm going to walk through how you would do this. What we're going to do is we're going to get the calculator. Which apparently is dead. Okay, now it's alive. And we're going to go to the lists. Let's see if I can, this where we can see both of those at one time. Now they're talking about using the sequence feature, and since you're never going to need to do this again, I see absolutely no reason to use the sequence. So we know that we're going to have rectangle number 1, and rectangle number 2, and rectangle number 3, and rectangle number 4. Okay? And then you can store the values of I in list 1, which is, of course, 1, 2, 3, 4. And then using the edit menu, the entries for x equals 1, for the first x sub I, the midpoint from 0 to 1 is going to be minus 0.5 plus the values in list 1. I will use that, but you don't have to. Because what you're actually going to do here is you're going to take the value in list 1, which is 1, minus 0.5. And here again, you could do that just as easily just by subtracting 0.5 from every one of these. 2 minus 0.5. So you don't have to follow their instructions. 3 minus 0.5. 4 minus 0.5. And there's all 4 of our midpoints, because your midpoint is exactly halfway between one interval and the next. And then in order to find, now this one, it actually is worth doing, because at this point, Y3 is going to be 2 times the numbers that are in list 2. No.
Okay, I was gonna say, because I just put it in there, number 9, and it did it for me.
Yeah. So if you do that, then what you're going to see looks like, where are we? Here, looks like this. And all you really want is the sum of those areas, actually since they're all 1 unit wide, you want the sum of 1, 3, 5, and 7. So you can go to your calculator and go to your list operations, which is second stat, and tell it to find you the sum. Where did my sum go? Oh, it's on math, sorry. Find me the sum of list, whoops, not there. Let's go down here at the bottom. So for that little problem, using the calculator is easy, and if you really did have to make 10 or 15 rectangles or whatever, then you could do it this way and get your answer pretty quickly without having to go through doing all the arithmetic. But I'm much more interested that in your learning what all of this means. So we're going to go to that. The total change, suppose we have a function x squared plus 20 that gives the marginal cost. The marginal cost, the rate of change of cost of some item at a particular value of x. Then f of 2 equals 24 gives the rate of change of cost at x equals 2. And that means that a unit of change in x at this point will produce 24 units of change in the cost function. Your cost goes up by 24 units. 24 cents, $24, 24 whatevers. And f of 3 equals 29, that means when x is equal to 3, that every additional unit of change in x is going to yield another 29 units in the cost function, and so forth. To find the total change in the cost function as x changes from 2 to 3, you can divide the interval from 2 to 3 into n equal parts and use them as we did in what we've been doing to get the total area and thus the total cost, the exact total cost. Now we're not going to do rectangles. We are going to use the integral from a to b of the function to get the total change. We're going to do the calculus, which is faster. So what we're actually going to do now is we're going to do an application problem. This is the introduction problem from the beginning of the chapter. This figure shows the rate that oil is leaking from a machine in a large factory in cubic centimeters per hour, with specific rates over a 12-hour period given in the table. And the total amount of leakage is over a 12-hour shift. Now, going through the table method, I've already filled these in for you. All you need to do is just fill in your x and y, or your y values. Using the graph, this is totally using the graph, then we're estimating, we can see that each one of these is, for the first one, we're going from 0 to 1, and then 1 to 2, and 2 to 3, and 3 to 4. So these are all 1 unit wide. So we've divided it up into 12 rectangles. The first one is rectangle 0, and the last one is rectangle number 11. And this first rectangle is 15.2 tall. The second one is 18 tall. The third one is 18.8 tall. The fourth one is 14.1 tall. The fifth one is 9.5 tall. And the one next to it's pretty close to the same, it's 9.6. So the heights are being read off where the tops of the rectangles intersect the function. So if we want to know the total leakage, all we're going to do is we're going to add up all those numbers in that table. And it turns out that the total leakage integrating from 0 to 12 is going to be 187.8 units of oil. That's the total amount it's going to leak. Even though the leak at various times sped up and slowed down. Even though the rate of change was variable. Now, we didn't do calculus on this, even though we used the calculus symbols, because we didn't know the value of the function. If we knew the value of the function, we could have approximated, if we'd known the equation, we could have approximated the value of that curve and had a formula for it. But that's the idea behind how you apply what we're learning, is we're going to actually apply the calculus to a real problem where the number means something. This one I only included because it kind of relates to one that we've done before, doing a derivative. You've got a driver traveling on a business trip checking the speedometer every hour. The table shows his velocity at several times. So at time 0, when he starts out, he's sitting still. But at the first hour, his speed is 52 miles an hour. At the second hour, his speed, his velocity, is 58 miles an hour. And at the third hour, his speed is 60 miles an hour. Now, what I would want to know from that is, how far did he go? Well, in the first hour, he didn't go anywhere. From 0 times 1, that's 0, because that's where he's still sitting still. But during the second interval, he went 52 miles. And during the third interval, he went 58 miles. And in the last interval, if you go from right endpoints, he went 52 miles plus 58 miles plus 60 miles, which makes more sense. Because if you go from the left ones, you're leaving out that last hour. So he went, the average of the two actually is how far he went. He actually went 110 plus 170, which is 280. He probably went about 140 miles. Okay? Now, honestly, you're not going to see very many problems out of this section. You have a little bit of homework in that section. Please don't start that homework until I get a chance to glance through it. But the reason I went through this is so that we could go through section 15.4 and you could see how to do what we're talking about doing. Okay? So we're going to wind this one up.